everyone, welcome back to another radio astronomy tutorial. My name's Eric Carlson, and we are going to be calibrating historical VLA data today using CASA. So right now I am VNC'd into the NRAO luster system. However, this works locally as well as on both a Linux machine and a Mac machine. So first thing that we're going to do here is we're going to actually secure our data. So we're going to open up a Firefox tab. And we're going to go to data.nrao.edu. So for the purposes of this tutorial, I have selected a measurement set that does not have any problems. There's no major flagging required. There are no transitions between B1950 and J2000, for example. It is a nice and clean measurement set, and this is just for the purposes of a basic calibration. So what we're going to do here is we're going to use the AC755, AC755 project code. So we'll scroll down here, we'll grab that. And again, the observation of which we will be using here ends in 410. So what we're going to do is we're just going to click the Select for Download button. And we'll scroll up again and we'll just click Download here. And what we'll do is we will put in our email and we will hit Submit Request. So what we'll do here is we're going to wait a couple of minutes and we are going to wait for this to finish before downloading it onto the luster. Alright, so after a few minutes, we are going to be presented with the following screen, and that's going to let us actually download our file in question. So what we're going to do is we're going to click the hyperlinked AC755, then we'll click the directory name again, the observation name, and what we're going to do is we're going to right click here on the .exp file. This is going to be our actual observation, and we're going to click copy link. So from there we can actually leave Firefox here and we can actually open up a terminal. So I have already created let's just do it this way. So what we'll do here is we'll just make a directory and we will move into that directory. And then what we'll do is we'll run wget and then we'll paste that link which we just copied. So once we've done that, we can actually start the data inspection phase. So what we'll do is we will load up CASA here, and I'm going to run a specific release. This is going to run 6.4.1-12 pipeline 2022.2.0.64. And the reason why I did that is because I've had some crashes with the most recent version of CASA, and this is the version of CASA that I run on my personal computer, and I've had good luck with. So once we're all loaded up here, what we're going to do is we're going to actually import our data, and that's going to be done using import VLA. We will use archive files. We'll be using a lot of tab to complete, so archive files, AC7 tab to complete gives me the observation file, so I don't have to write all of that. And then what we'll do is we'll define our visibilities, so viz equals, and this is the name that we're going to carry on for the rest of the observation, so AC755.ms. And we'll just hit enter here. Now, what we can see going on in the background in our logger is that we're actually importing our data, and this is going to provide information on the scans. Now, we don't need to capture this information as it kind of comes through, because the next step in the phase is to actually list our observations. So what we're going to do is we're going to do the list obs command to list our observations. So list obs, and then we're going to use viz ac755.ms, and we will tell it to write the information to a file named listobs.txt, and we will hit enter. So what we'll do here is if we open up a new tab and we go back to that directory and we type nano, we can actually see our observation list. So as we can see here, we have our observation information at the top, followed by our scans, followed by our actual fields. Now, as you can see, this measurement set has two different spectral windows, which we could perform calibrations on. For the purposes of this observation, we're just going to do L-band observations, so that's going to be spectral windows 0 and 1. So, while we're here, the first thing that we're going to need to do is identify our fields. So, first things first, our flux calibrator. That's going to be 3C48. Second thing is we need to identify our target. For this tutorial, we're going to be using field 6, J0121, and now we need to identify the calibrator, the phase calibrator that goes along with this source. So for the purposes of this observation, what we'll do is we'll go up and we'll check the scans. So here is our target, and for modern EVLA observations, what you'll see is you'll have, so I'll give a spoiler here, field 5 will be our phase calibrator. So what we would see is we would see field 5 observed, field 6 observed, and then field 5 observed. Now, that is not the case in this observation. That is okay. But what we know is we want to pick a phase calibrator that is close in space and close in time to our actual target. So for the purposes of this, field 5 will be our phase calibrator. So once we have all this information, we can go back to our CASA tab, and we're going to fill in all this information. We're going to take advantage of Python, of being in the Python environment, and we're going to define some variables. So first thing we'll do is we'll define our flux calibrator to be field 7. Our target space is field 6. Our phase calibrator is field 5. And then our flux, the string containing our flux and our phase calibrator is just going to be 5, 7. Now, we need a reference antenna. And to do that, we'll run plot ants viz equals ac755.ns list file equals, excuse me, we do not need that here. So we'll just plot our antennas and we will get a figure that pops up here. Now, we want to pick an antenna that is close to the center of the array. I can tell you that VA06, which is here in tiny little print, is going to be our reference antenna. So again, we're going to take advantage of being in the Python environment, and we're just going to define that as antenna equals VA06. Perfect. So once we've done all that, it's time to inspect our data. So what we'll do is we'll run plot ms. We'll define the visibility. We will define the field that we want to take a look at first. So let's do our flux calibrator. And let's just load that. All right, so once everything's loaded, we notice a couple things here. We have all this data up here. We have data down here, kind of in the dumps, and then we have a second scan right here. Now, there's a couple things that we know right off the back. The first thing is we know that this is all of the spectral windows, because I did not define a spectral window selection. So if we just want to look at L-band data, we'll define our spectral windows 0 tilde 1 for all spectral windows between 0 and 1. There are only 2, so we could also do 0, comma 1. So if we click plot, now we see we just have that first scan, but we still have that data kind of way below our data up here. That is going to be our cross-hands data, and I know that because if I go to correlation over here, and I do RRLL for our parallel hands, and I click plot, that data goes away. It is important not to accidentally flag that data thinking it's an erroneous antenna without first double checking that that's actually your cross-hands data. We won't be doing polarization in this tutorial. That'll be left for a future tutorial. So we still have a time plot here. We can actually run over to our axes tab and change this to our UV wave. So that's going to be our amplitude plotted against our UV distance measured in wavelengths. And what we can see is we can see kind of this typical steep spectrum source for our flux calibrator. And yeah, for our flux calibrator here. We can also go and we can change back to data, and we'll take a look here. While we're here, we know that our phase calibrator was field 5. So we'll click plot, and we have that very typical kind of flat spectrum plot for our phase calibrator. Now, as you can tell, I'm not doing a lot of flagging here. I'm working with this data as it is. It's pretty well behaved. But if we did want to flag any of this data, we click this little box down here with the green plus mark. We would draw a box around the data we want to get rid of, and we would click the flag button. If we want a region that we want to get rid of, we can click clear. I'll cover flagging and advanced calibration in a separate video. So once we've done all of this, we can actually go back to our data here, and we can run set JANSTI. So this is going to set the model for our flux calibrator. So we'll run viz equals AC755.ms. Our field is going to be our flux cal. Now this adverb, if you will, this function argument has changed in recent versions. It was previously mod image, and this is going to be mod image 3C48 _L.im. And what we'll do is we'll do scale by channel, and we'll set this to true. And we'll run that. So this is simply setting a model for our flux calibrator. And we kind of get that report provided here. So what we'll do is we'll actually do our zenith angle dependent gain curve calibration table first. So this is going to be a general calibration, so we'll run gencal. Again, viz equal to AC755. We will do our cal type is going to be GC, and we'll write our results to a cal table, and that's going to be gc.cal. And we'll hit enter and run that. Once we've done that, we can do our complex gain calibration. So we'll run gain cal is equals AC755.ms. We'll do a cal table. This is going to be where we're going to write our results of this week. Cal table is equal to cal.g. We'll perform the following operations on the flux and phase. And we will define a solution interval of infinity. So inf, 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 We will define our reference antenna to be the antenna that we picked earlier, and we need to carry the solutions from before, so we'll set our gain table to be, this is a variable assignment, gc.cal. And we're going to run append equals false. So again, we can see that our solutions were written here in the background. We had we found 3 solutions, 3 were attempted, and 3 succeeded. So once we've done that, what we're going to do is we're going to now generate our flux, our fluxes, our flux table. So we'll run flux scale. So we're going to now define the. We're now going to use our flux calibrator to find the flux value of our phase calibrator. So again, we'll use flux scale. We'll set viz equal to myviz. We will run, so this is going to be cal table equals cal.g. We need to reference our flux calibrator. We need to transfer that solution to our phase calibrator. We need to write a flux table of cal.glx, and we want to set append equal to false. Excuse me. As we can see, we can define variables, typically with long variable names. I'll set the visibility, so this is going to be AC755.ms. Great. So here we can read all this information, but we can also go to the output, and it condenses it a little bit better for us. We see that for spectral windows 0 and 1, the ones that we are primarily focusing on for calibration, we had a high signal to noise over 400, setting our flux calibrator between 2.24 and 2.3 Janskis. So once we've done that, we like our solution. Now we're going to do our baseline calibration. Now, this is only required for transitional VLA data, but does provide an incremental improvement in your calibration for regular historical VLA data. So this will be BLCal, again, viz equals AC755.ms. We're going to write another cal table, cal.bl. We're going to perform this on our flux calibrator, our solution interval, flux cal. Our solution interval, again, will be infinite. Our reference antenna will be our reference antenna. And then we want to pull down the table that we just generated. So that's going to be gain table equals cal.gflx. And then we want to interpret that table using a nearest solution. Let's see here. Oh, no, my apologies. We don't have a reference antenna in this command. Let's try that. There it goes. Okay, so once we have that, we've generated all the calibration tables required for actually calibrating this particular source. So once we've done that, we can actually apply the calibration tables. So what we'll do is we'll run apply cal, viz equals AC755.ms. We will set the field equal to our target. We are going to use the gain tables that we've generated, so these are going to come in as a list. So we'll use our cal.gflx. The second entry, cal.bl. And then we'll do gain field, and this will be our phase calibrator. Great, so we've applied our calibration to our data. Now, what we'll do here is we'll go back to our plot MS that we had over here. So what we can do is we're going to change our field to our target, so it's going to be field 6. And we're going to go to our axes. We have our UV wave, and we want to change under amplitude, we want to change the data column to corrected. So we'll plot our data. So here is our corrected visibilities. Everything looks good. Nothing seems like it needs to be flagged immediately. We can actually go to time and just double check. Nothing looks spurious here. That's not otherwise explained in the UV wave plot. So let's go back to that plot. And so from here, we can actually start imaging. Now, for VLA data, I like to image in diffmap. So what we'll do is we'll run export UV fits. Again, we'll run viz equals AC755. We'll define the fits file. So this is going to be J0121 plus 0347. It's historical VLA data. It's A array, L band, and this comes from our AC755. This is just my personal naming scheme. This is going to be our target data. We want the corrected data column. We want to pad with flags. And if we had previously written, we can set overwrite to true. And given a half second, that will export our data to a UV fits file, which again is in our working directory as we see here. So in the next video, I will try to review some more complex calibration and flagging techniques. I will also make a video on imaging the source in diff